and get started. Good morning, thanks for coming. So I'm using the slides and I'm sort of extending the talk given by the middle person, Colin, who is a student who as an undergrad started in Notre Dame was David Jiang, and now he's at CMU. This was a talk for UPSLA a couple of months ago, and now we have more time and less preparation on the part of the speakers, so hopefully y'all will ask more questions about all the parts of this work. So I'm talking today about probabilistic programming, so it's sort of obligatory to begin by acknowledging that, especially nowadays, it's in vogue to write programs that compute with probabilities and also more generally expectations of probability distributions. And maybe for our current interest, it's most important to work on natural language processing. It's kind of a blessing and a curse that people often ask me if I work on ChatGPT nowadays, but also other applications like computational biology go back to the last century. And the main issue with all these applications is that you have some idea you want to express, which is generally you have in your head some kind of probability distribution you want to compute with, but by the time you actually get it into code that can be run in some conventional programming language, you've done a lot of math, you've done a lot of sort of simplifications that are domain specific. So by the end, you have code that looks nothing like your idea. So if your ideas change a little bit, then your code changes a lot, and then you have to basically rewrite your code. And that is tedious and error prone, that kind of manual coding. But you kind of have to do that if you want efficiency, if you want to have the flexibility to model a variety of, say, grammars or, I don't know, genes or something. So that's where probabilistic programming languages are supposed to come to the rescue. They allow you to write the model, which is much more closely related to the idea in your head. And then the promise is that you just compile it to some kind of efficient inference code automatically, so that's no longer tedious and error prone. Okay. Now for especially our interest, there are three things we want for a probabilistic programming language. The first thing is that it should be expressive. It should allow us to express ideas we have. And when it comes to things like natural language processing especially, but also natural processes like the evolution of some dynamic system, recursion becomes a natural way that we want to express our models. So recursion including loops, but not just loops, because you have tree structures in natural language processing, computational biology, and a lot of times people may do without when they find it too hard to write the code, but we still want to express these things such as probabilistic context-free grammars. That's the first thing. And I'm starting to show this table that compares our programming language, PURPLE, which stands for Probabilistic Exact Recursive Programming Language, to other more established probabilistic programming languages. And some languages are expressive, like WebPeople allows you to write probabilistic context-free grammars. Other languages are less expressive, like DICE. But in exchange, what DICE allows you to do is to do exact inference, that you can just compute the exact number, which is like the probability or the expectation of some quantity, whereas with WebPeople, when you try to be expressive about your model, you end up with just approximate answers to your queries. And that can be not just a matter of exactness, also getting close to the answer. It could actually affect whether you can compute the answer at all when the answer is like the derivative or gradient of something. So nowadays, people don't just handwrite their probabilistic context-free grammars. They want to learn how a neural network might be able to generate the weights used in the grammar. So for that, you need to do gradient descent, which means that you need to take the derivative of some loss function with respect to the weights. So it's important that we not only be able to compute the probability, we also can compute some derivative of the probability. And that often calls for an exact inference method, which WebPeople doesn't provide, but DICE does. So PURPLE allows you to do exact inference on both recursive functions and recursive data. And it actually does it faster with less memory use and less time use. And that's because we're able to turn an expressive model into a polynomial time algorithm analogous to what's been discovered previously in the literature by manual coding. And so you can kind of see this is actually I think the vertical axis is the log scale in time, and the horizontal axis is the problem size. So maybe the purple line looks like it could be a polynomial line. Okay, but we're not really claiming that it's polynomial, but it's certainly a lot better than the other lines, which are just shooting up there to the left. Okay, please feel free to interrupt with any questions. So the key to our achieving this combination of features is that we're actually using a linear type system to ensure that the compiler can perform correct transformations. And that linear type system ensures that every bound variable, every local bound variable is used exactly once, which means that we don't discard probability effects and we don't duplicate probability effects. Okay. So the general organization of our implementations, we start with a program, and then instead of using operational semantics like people usually do, our implementation actually uses the denotational semantics to turn the program into a set of equations which are recursive. But those equations are just numbers now, so we could just use some kind of numerical solver to solve that equation. So some kind of numerical fixed point, maybe just fixed point iteration, maybe Newton's method, but that's not so crucial to the talk today. So I'm basically going to assume that you have some system for solving these equations, and then you get some exact distribution and its derivative out. Okay, so let's look at this simple example. Suppose you have a probabilistic grammar at the top of the screen, and we just want to know the probability of this probabilistic grammar terminating at all. So what do I mean by terminating? Well, there's a p there, which is a probability between 0 and 1. So imagine that p is 1, right? So if p is 1, we're just always using the first rule, and we're never using the second rule. So if your only rule in the grammar is s goes to ss, then you're just going to keep rewriting 1 to 2 to 4 to 8 s's, and that will never terminate. So if p is 1, then this grammar would never terminate. So its probability of generating a finite string will be 0. Whereas if p is 0, then we always just go s to a, and the termination probability will be 1. Okay. Now, if you p somewhere in between, then you might generate a tree like this, and on different rounds of the program, you generate some other tree, and sometimes it will terminate, sometimes it won't, and that's the question: how often would it terminate? So to answer this question, we can write this purple program. So the first thing it defines is just a way to flip a coin, where it gives true with probability p and false with probability 1 minus p. And then the second part of the program is more like the grammar, right? So it flips a coin to decide whether to use the first rule at the top and the second rule at the bottom, right? And this program always returns unit. So the answer we want is just the weight of unit. Yes?
There's this s function.
Yeah.
And then there's this factor function. And I'm not seeing where s is called, and I'm not seeing where factor is defined. Are they? Is that a typo or?
Okay. So thanks. So there's two questions. One is what is factor, and the other is where is s called. So I think the slide is missing at the very bottom a call to s. So there's kind of the main program after all these global definitions that says s unit. That's the initial call. And then factor is a primitive, so I'll get to that in a minute. So one way to think about how this program works is to look at some operational semantics that rewrites the program with weights. So that should be somewhat familiar to some people in the room. So we start with the initial call s unit at the top. Okay, that's missing from the code on the left. And then we beta expand the call to s. And then below that, we beta expand the call to flip. And then we come to this also primitive emb, which just means summing two distributions basically, or here it means non-deterministically rewriting to two branches. And then on one branch, factor p multiplies the weight of the branch by p, and on the other branch, factor 1 minus p multiplies the weight of the branch by 1 minus p. So we now have two branches, and one branch rewrites to true, the other branch rewrites to false, and then we just do the if. And in one branch, you get 2 calls to s. And if you keep doing that, you get 4 and 8 calls to s. On the other branch, you get termination. Okay, yeah?
So when you say probability of finite string, I mean what's the sample space? Like all finite and infinite trees? And not...
Right, so here for the operational semantics, we're sampling all the ways to rewrite.
Sure.
Yeah. Right, so that's the operational interpretation, which might be more intuitive to some people.
Right.
Now, if you, like some other people, prefer denotational semantics, then for each expression, there's a type, which is the domain that its eventual values can range over. So that's a sample space. But then that might not, if there's no termination, then there's just no, like this whole thing, this whole program is going to denote a distribution over a unit.
Right.
And that's just only having one weight, and that weight is the probability of termination. And so if it doesn't terminate, then the weight at unit is just going to be less than 1. And that's the weight that we want to compute.
Okay. So it's the probability of this term.
Yeah. So when the expression terminates and gives an outcome, there's some weight there. If it doesn't terminate, then there's just no weight there. Yeah. Okay. Great. So so unlike a lot of maybe general purpose programming language compilers, we will implement the denotational semantics. So what you just saw on the previous slide, like this operator semantics doesn't appear in our compiler at all. It only appears in our proofs. Right? Our compiler just thinks about denotations where every expression can be denoted distribution that doesn't necessarily sum to 1 over possible outcomes determined by the type of the expression. Right, so if you have a Boolean expression, then it denotes the distribution over Booleans. For example, true denotes the distribution that has weight 1 at true and 0 at false. That's the top 2 lines. And then unit denotes the distribution over unit, and it actually gives weight 1 to unit. And you can write some non-terminating thing, like an infinite loop, and then if that has type unit, then we'll just denote the 0 distribution over any type. Yeah. Okay, so those are like the base cases. And then we can start to do our usual compositional denotation thing. So like if you have an M, then you're just summing the 2 distributions, so you're summing the weights. If you have factor, they're just multiplying. So this expression that appears in flip is just going to be a linear combination of the distribution that true denotes and the distribution that false denotes. Right? Okay, and then we keep going. Like what does semicolon mean, or what does let mean? It just denotes the kind of the product of 2 distributions. So here there are 2 distributions over unit, so it's just one weight which is equal to the weight times the weight. Okay. So if you take all these expressions, all these equations, and do substitution until only one variable remains. So the variables are, I should clarify, there's 2 kinds of variables. There's purple program variables. Actually, there's none on the left-hand side, but maybe using flip and s are kind of like a variable, right? You can have lambda-bound variables. That's one kind of variable. But on the right, in the denotational semantics, the variables that the equations talk about are things that look like double bracket expression subscript value. So the probability that a certain expression gives a certain outcome, that number is a variable as far as the equations are concerned. Like the bottom line there right now, that's a equation relating one variable to the square of some other variable. Right? So you kind of have to squint and treat. Every time you see double bracket subscript something, you squint and think, oh, that's just a variable in the sense of equations. That's the variables that are solved to get the exact distribution. So if you start to solve these equations by doing substitution, okay, there's also if, whatever, and then you get this final bottom equation, which is just over one variable remaining, right? So that variable is the probability that S unit gives unit, right? So this is now the variable, and the variable, let's call it W for I don't know what, but that variable equals P times W plus 1 minus P. So it's just equation over W now. P is a constant, right? So it's just an equation over variable W, and you can solve it. It's actually, you can use a quadratic formula or whatever, or you can do fixed point, solve for least fixed point, and then you solve for W, and that's what happens. Yes?
So I'm trying to understand the top line expressions of value plus probability. So you fix it for every type. You fix a type, and then it's like an expression of that type, of the value of that type.
Yeah.
But one possible value would be bottom or something? Like
No, there's no bottom, right? So the type here, like if it's Boolean, let's say, then the only two possible values true and false.
Okay.
Yeah. So every every expression of type bool in our language will denote a probability a distribution.
Oh, I see. But true, sub-true, and sub-false may not add up to 1.
Right. Sub-true and sub, like here it adds up to 1.
Right.
But by the time you get to W, like W may not equal 1. Right?
Well, but I mean, like if you have some non-terminating, some potentially non-terminating thing, then sub-true and sub-false will add up to the probability that terminates.
Yeah. So it may add up to more than 1. Like if I say factor 5 in, what's the syntax here? Factor 5 semicolon true will add up to 5. Because it's just multiplied by 5, or factor p semicolon true adds up to p.
Yeah.
Right? And that's adding up to more than 1 case, and you can also make it not add up to less than 1. Like in fact, there's a primitive fail that will just give you a 0 distribution, or you can write the infinite loop as equivalent to fail. Yeah. Yes.
Will there always be a finite number of denotation variables?
Is there always a finite combo of denotation variables? Thanks for inventing the term denotation variables. Sorry, is there a finite combo?
Number, not combo.
Combo.
No, it's number.
Number, yeah, it's always, that's a great question, because this whole piece of work is actually about dealing with the case where it's an infinite number. Right, so right now there's a finite number, right, like 5 or something, but we're going to want an infinite number conceptually. Because suppose you write a distribution over trees or strings or natural numbers, right? The domain is infinite, so even though the expression itself is like a finite length that has infinite number of possible values, then you have an infinite distribution, and each element in that distribution is a denotation variable. Yeah.
There was a question regarding the random factors.
Yes.
Is it statically checked if the factors sum up to 1?
Do we check this factor sum up to 1? No. So here, it's totally because the programmer liked it that the programmer wrote p and 1 minus p. In fact, in the earlier version of the slides, in the paper, we just put p and q. And sometimes p plus q may not equal 1. Yeah, it's not restricted at all. So there's nothing really special about 1 here.
Is there a weight?
They're just weights. Yeah.
Okay.
The weights may not sum to 1. Yeah. Okay.
And so what is p? Is it a free variable?
Single p as a meta variable. Single p as a meta variable, just put 0.3 every time I write p, basically. Yeah. But p is something. Yeah. Okay. So yeah, you can just think of p right now as a literal, like someone is going to go through these slides. And
Put a literal in there.
Yeah, put a literal there. Now, what our language least implementation allows is you can actually have you can write a partial program, it turns out, that doesn't say what flip is. So when we want a derivative, what we say is we take a derivative of, let's say, w with respect, here you want to take the derivative of w with respect to p, basically. That would be nice, right? But what we actually take derivative with respect to is not p, but flip. So flip is a distribution. So instead of taking the derivative with respect to p, we just leave the whole flip out, and we say, well, I don't know what flip is, but you can compute the gradient of w with respect to all of p, the two numbers that make up flip. Sorry. Hey.
In fact, I have a question about the equation solver. So when we convert the program into a group of equations, is that possible? Sometimes this group of equations have no solution. Because now we're using a numerical method to solve the equation. But
great.
Yeah.
So the question is, when you solve, how do you know this is going to produce a solution? Maybe there's no solution.
Yeah.
I mean, it's at least fixed point. So mathematically, there exists a solution. And then if you solve, even just using fixed point iteration or using Newton's method, it turns out there's these people who wrote very nicely written papers showing that it will converge to the least solution. This is like some theorems that even take into account floating point rounding. I don't know how they do it, because I want to read the abstract, but somehow they do that. Yeah. And it also works for any semi-ring. By the way, it's not just numbers. Okay, yeah. So we're here for the least fixed point. Okay. This is just one question you might ask about this grammar. So let's look at some other questions. Maybe the most popular question will be, same grammar, but what if I don't just want the probability of it terminating at all, but the probability that it generates a particular string? Well, here, strings are only made of A, so it's basically the probability that the generated string has a certain length, right? So maybe I want some distribution over length. Okay. And you might have other questions, like you might have a finite state machine, and you wonder what's the probability that this grammar is going to generate something that is accepted by the finite state machine. Right? So that's a popular thing to do because you want to maybe look at possible ways to complete a sentence generated by the grammar. Right? So like, in principle, when you write some email and the email client completes your sentence, it's doing that. It's taking the prefix that you've already written and asking, what's the most likely next word, or what's a likely completion of the string. Okay, so to answer all these questions, we start to want to express distributions over strings, and also over possible lengths of the strings and things like that. In part because we want to express these questions in a modular way. So we want to write a grammar and write different questions, and you want to be able to change the grammar separately from changing the questions. So you want this kind of modular composition. So here's, I think, the natural way to write this code. So we start by defining some types for strings that are generated by the grammar and the length of those strings. Okay, so the two types are string and nat. And now these types are recursive. They have infinite domains, and we haven't even defined what these types denote. We just write those type definitions. And then if you have defined a string type, you can write some code that generates those strings. And if you define a nat type, then you could test whether the generated string has a certain length. And what's nice about this code is that the two pieces, the top half and the bottom half, basically, you can just compose them as functions to get the main program. Right? So the main program is just, generate some string and check if it has the length 3. Right? If you want to ask a different question about the same generated string, you just don't change this part, change the outside part. But if you want to generate strings in a different grammar, you just change this part and don't change the outside part. Right? So you could do this kind of modular composition, and we like that. Okay, but this requires us to write programs with recursive types. And the problem is that these recursive types, if you really want to say what they denote, they're infinite domains, and now we have to solve equations over an infinite number of variables. And that we don't want to do that. Right? And that's not what people actually write code to do. Right? So it turns out that people can, they've written lots of papers about how to compute exact, parse probabilities. And what they do is they solve fixed point equations over a finite number of variables. Right? But what are these variables? Like, what are these finite number of denotation variables? How do we come up with them? So one way to think about our work is we sort of systematize the ways in which lots of previous papers have made these kinds of problems finite. Okay, so we make a compiler that will replicate previous papers where they end up with some kind of polynomial time algorithm that just does some kind of even dynamic programming or fixed point iteration. Okay. And there's basically two ways that we've come up with, which are different program transformations that will turn the recursive types into non-recursive types. Right? So the strategy is we start with some program that the programmer wants to write, then we're going to apply these transformations until hopefully we get some program that only has finite types, and then we reduce the problem to the previously solved problem. That's the strategy. Okay. So that's actually the main contribution of this work. Like everything I said until here is like known, and people, we know we want to write these programs, we know how to solve once we have finite domains, but how do you write infinite domain programs and have exact solutions? Okay. So let me just show you the two transformations by example, because the program on the screen right now doesn't run directly. it actually does run directly in the operational semantics, but that only happens in our proofs, right? So what doesn't happen in the implementation is that that operational semantics. Our implementation is going to start with this program and going to apply 2 different transformations each time to eliminate a different recursive type. So I don't think the order really matters, but let's just do the NAT type first. Let's eliminate the NAT type. And the transformation is something that we call defunctionalization, and we can debate whether this name really makes sense because what's being eliminated here is not a function type, but a recursive type. So, I think some reviewers want us to call it de-recursivization or something, but it's the same idea, right? So you look at a type, it's recursive, you want to get rid of it. So let's look at all the places where we introduce values of the type, right? So this NAT type has 2 constructors, suck and 0. So you go through your code, you look for all the places where you see suck or 0, and you just name those places, those sites of construction, those sites of introduction. So let's call them L0, L1, L2, L3. And then you do this whole program transformation where you take the labels L0, L1, L2, L3 and turn them into a new, do I have pointer? Oh yeah, I have pointer. Then you turn it into a new type lock, which is not recursive, because you're just enumerating the finite number of places in your code where you used to construct NATs. Okay. So basically, we're replacing a number by the closure of how we plan to construct that number. So we are kind of delaying the construction of the number. So instead of constructing a number, we just remember how we would have constructed it, and that's some finite amount of information. And we delay that construction until we're just about ready to pattern match on it. Right? So every time the old code pattern matches a number, like here case n, is going to become case unfold n, where unfold just remembers, oh, here's how we plan to construct that number in the first place. Let's construct but immediately destruct the number. So we never really construct the number. That's how we get rid of the number. Right? So all the construction code that we used to have in the lower left now goes into different cases of this new unfold function. Right? Unfold is if you're familiar with defunctionalization, which I encourage everyone to be, this unfold is sometimes called apply. Right? So before with defunctionalization, there's some function type we want to get rid of, so we take all the lambdas in our code and we turn them into constructors. And that new type, the non-functional type, is pattern matched in this new function called apply. Whereas here, we're getting rid of the recursive type by replacing its constructors that are which are pattern matched in the unfold function. That's new. Okay, so that's defunctionalization, and that allows us to get rid of NAT, because the new NAT type doesn't have suck NAT, it just has suck lock. So now everything's finite. And if you're still tracking like what this code means after the transformation, you can think of the lock as like a location in the string we're trying to parse. So L0 is kind of like saying the beginning of the string AAA we're trying to parse, and L3 is like the end. So because there's a 3-letter string we're trying to parse, AAA, there are 4 locations in that string, and those locations correspond to L0 through L3. Yes?
Is it always the case that you know what it is starting? Like, I mean, what if that number is generated like at runtime?
Yeah, so is it always the case that you know like L0 through L3, like what if this is generated? Yeah, right now the only technical answer we have is you wait until you know the string you want to parse before you apply this program transformation. So you actually stick a literal string in here, because until then you don't know. Yeah, and maybe there's some hope for future work about can you do some kind of polymorphic? I don't even know if you should call it polymorphic, but some kind of staged defunctionalization where you say, well, I don't know how long this string is, but I know it's going to be this form. Right? Like if you know the length of the string, then you can do this. Like if you don't even know the length of the string, that's interesting. But right now we just wait until we have the actual string, and then we call the compiler. Sorry, I think Jeremy had a question.
I had the same question.
Oh, great. Hey.
Okay. What if you had like a function
that took any mat, and then like the successor to that mat. Like it could be multiple different.
Right. So
how would that?
Yeah. So suppose that in your source code, there's a place where suck n appears, or some suck, but then the argument to suck has some free variables in it. Then we would transform that to a lock type that has, I mean here the locks is just an enumeration of 4 possible values, but then we'll actually put the nat or whatever here as like an additional, So in general, you get a sum type, but the sum type may not be over units. Yeah. Yes.
If you map in the law, would you make it mutually recursive with navigating?
Yes, but it's sorry. Do I put nat there? Oh, okay. There's 2 things. Yeah, I shouldn't. Okay, I think I spoke too quickly. Sorry. If you have suck something, if your construction expression has any free variable, then what we're doing is to put those free variables into like a closure, right? But if one of those free variables have type nat, then yes, we will get mutual recursion. That's not what we want. So then defunctionalization doesn't work for our purpose, right? Like it will work to produce the same like operationally equivalent program, but it doesn't work to eliminate the type nat. So we don't want to do it. So that's a precondition for our use of defunctionalization, right? So sometimes transformations don't apply, and sometimes if you like, it looks like a transformation that would apply, but then you apply another transformation, and it makes this one not apply, right? So that's like the worry, right? Like, what if I had to do some kind of search to, like, in principle, there's maybe a magical sequence of transformations that will work, but how do you find it? Right? So that's a worry that maybe in a few minutes we'll get to. It's kind of a good answer, but decide how good it is. So indeed, that the loop, right? Okay, so that's the problem. I forgot to turn that part off. Let me turn that off. Okay. So, but first there's another worry, which is what if by moving this code around, what if by moving, what if the argument to suck has some kind of probabilistic effect in it? Right. So you're moving the code from the construction site to the pattern matching side, but then what if that pattern matching never happens? Then the probabilistic effect never happens because we're basically delaying whatever effects there are in the introduction until elimination. Or what if the same code gets run twice? Now you're duplicating the probabilistic effects, right? So for those reasons, we need to impose some kind of linear type system that says you can, once you create a nat, that nat will be consumed exactly once, right? So this way we move the effects from production to consumption, but that's fine. Okay, so that's one transformation. The other transformation is what we call refunctionalize, but again, it's just used to target a recursive type. And this time we look at a recursive type like string, and we look at all the places where we pattern match on it. Like in this code, there's only one place where we pattern match on string, which is in Hasna. Like here's case W. Right, so that's where the only one place where we pattern match on string. And then we take the 2 cases, or however many cases the pattern match has, like here's nil and const, and we turn them into new functions. So instead of constructing an actual thing that to be deconstructed later, we just construct a function that would then be used whenever the string gets consumed. Right, so we're kind of moving the work from so refunctionation is moving the work from consumption to production. Right, so I look ahead to, I'm making a string, but I know how it's going to be consumed because it'll be linearly consumed. So I know eventually the string I make is either going to be a nil or a const. It's going to be consumed here. There's no other place where I consume it. Right, so I know it's going to be consumed here. So I might as well, instead of constructing a data string, I'm going to construct a function which can be called to perform this pattern matching. So why is it a function? Because why is the function from walk? Because this case expression on the left has a free variable n. So n here, the log is n. That's a free variable that goes into that pattern match. That's why it's a log. Actually, n is a nat, but anyway, it's really maybe it's nat actually. Come to think of it. Anyway, but it's either way. Yeah, I think actually it should be natable. The nat is finite now. It's just a log. That makes sense. Yeah.
So does this mean that like if you have data type like string, you can only use it in one place in the program?
If you use it in multiple places, then we get not a single function, but you get a tuple of functions. But it's the reason we avoid that here, to keep this slide simple, is that tuple is kind of a special tuple. It's what in linear type systems is called, well, I don't know, maybe called additive tuple. It's like a tuple that's often written with an ampersand instead of a circle times. It's a tuple where when you consume that tuple, you have to choose which component to consume it by. Like you can only choose one component. You can pick, I want this component, then you don't get the other ones. Whereas with sort of the usual tuple, when to consume it, you get all the components back. But here you get only. Did I run out of battery? Oh my god, it's annoying. Well, let's see. Okay, sorry,
Can you try using the desktop?
I have, I don't know if I have the way to restart this, but it's okay. You know, you've seen all the important slides. I don't know if this will help, but if it doesn't, then it doesn't. I don't know. Anyway, yes. So just give it to.
So you're saying it would be like log arrow, like bool with nat or something?
It's the tupling
Or
is
something.
outside the arrow, so it's a tuple of functions. Yeah.
And the arrow is actually a lolly?
Yeah, we'll get to that, but it's actually a lolly, and in the paper it's a lolly, but yes, got it. Okay. Other questions? Good way to cut off questions.
So
Yes.
till your computer restarts, like can you give a small example of like effect duplicating? I mean, I didn't quite understand what.
Like what does a linear type system prohibit you from doing?
More like what is the probability and what does it mean to duplicate?
Okay, right. So what we don't want, that, I mean, it's not in the slide, so that's good. I'm just going to use the board. Yay. What you don't want is, suppose I have something like, let n be suck, and then here, I don't know, I just put fail for all I care. So this is, I mean, if you think about running this code, it's just going to fail, right? Or, okay, maybe we don't fail, here we use m to choose between two numbers. Like instead of writing, like, okay, I'm going to write suck, it's either 0 or suck 0. Right? So this is either 0 or 1, so this is supposed to mean something like either 1 or 2, right? And you might do something like n plus n or something, right? Now, is this supposed to give, if this overall is going to be 1 or 2, then this is 1 or 2, but then you're doubling a number that's either 1 or 2, so you should get only an even number, right? If you kind of follow the usual intuition about how these programs run, the result of this program should always be even, right? Because you're choosing a number and then you're using it twice, right? But now if I defunctionalize this program, so I'm just turning this program into let n equals some L, which L represents this whole expression, right? And then here I'm going to be like, oh, I'm n plus n, which is going to turn out to be like n-fold, n plus n-fold. Actually, the unfolding is going to happen inside the plus, right? I write some plus code. The plus is going to deal with pattern matching on n. But basically, it's going to unfold the same L twice, and now this might return an odd number. Because maybe when you unfold this, it's going to do some point flip to choose the 0, and then when you do this, you're going to choose sub 0. Right? So each of the unfoldings of M might give a different result, and that will be bad. Because now you've changed the operational behavior of the program. Because this is always even, this is sometimes odd. Yeah. So that's what we don't want. So in fact, our type system is just going to say you use N twice, that's not allowed. Yeah.
Thanks.
Okay, thanks. That's great. Okay. There's really no technical detail in the remaining slides, so I can just tell you what's going to happen. First of all, there's a question of what happens if you do some kind of how do you find a sequence of transformation that works? And when I say works, I mean without encountering that kind of mutual recursion problem that you will get if you try to defunctionalize a map, but the construction site contains, like if this is suck of n prime, where n prime is itself a map or something, right? It turns out basically that there's an algorithm that if there exists a sequence of transformations that works, we'll always find it. And it's just a greedy algorithm. You just look for some type you could eliminate that doesn't have any free variables with recursive types, and then you keep doing that until hopefully you finish. And the theorem is that if there's any sequence of transformation that works, then this greedy way will find some way that works. Okay. But maybe there's no sequence of transformation that works. Okay. And that's kind of to be expected because instead of writing a probabilistic context-free grammar, you could have written a probabilistic Turing machine, and then you'll be like trying to compute the probability that the Turing machine terminates. So and indeed, if you try to write that code, our type system will reject it as being nonlinear. But sorry, not the type system, the transformation. Oh no, it's also hard to write it. I think you can write it. No, you can probably write it in a linear way, but we will not be able to find a sequence of transformations that works on that program. Okay, so and that's like the best characterization we have for when there's a sequence of transformations. Like we don't really have a crisp way to tell other than by trying with this greedy algorithm. Okay, so that's one question. Yes.
Related to that.
Yeah.
Well, I guess I'm wondering. So, like in a traditional language setting, I could ask, like, do you find out at compile time or at runtime? Now, does that? I guess my first question is there that distinction? And then if there is, which is it for finding out if? I guess transformations are compile time.
Well, yeah, like if you remember the pipeline at the bottom, right? So the transformations happen first on the program, right, and they happen before you do the solving. So if by runtime you mean when numbers actually start to be added and multiplied, right? That's before that. Yeah.
Or do programs have input in the system?
Yeah.
That's also a distinction between runtime versus compile time.
Yeah, but
compile time is before you have your input.
Right. So
is that distinction here or not?
So let's look at different kinds of input, right? So for example, someone's asking, what if I don't know what string I'm parsing, or I don't know the length of the string I'm parsing, right? So right now, that will have to be in the program. Like at least the length, and maybe even the actual string you're parsing is in the source program. You literally I think I have some PostScript to generate that program, and then it gets compiled, right? So in principle, there's no general theorem that says if parsing a length 5 string will work through the transformations, parsing a length 10 string will also work. I mean, we kind of know it will work, but there's no, so that in that sense, compile time is pretty late, right? Because it happens after this kind of input, right? But there's another kind of input which can be supplied later after those transformations are known to succeed, which is the actual distributions. Like it turns out that if you have different weights for your grammar rules, or those are just tensors input to PyTorch or so you can actually support that after the compiler. So there's different kind of inputs. But of course we want. Yeah.
And is there a way to sort of so those can vary? How do you refer to those in the program?
To
those.
The later inputs. Yeah. I showed you one way to define a global distribution called define. There's one other way to introduce a global distribution which is called extern. Okay. Right? And and that name is supposed to be suggestive, right? So you just write extern flip, and you don't define flip, and you're expected to supply flip later.
Okay.
Right. Right. What else was in the slides? I want to come back to the linear, or the lollipop, the linear functions, because they actually are key, not just for ensuring that the probabilistic effects are dealt with correctly, because they're not deleted or duplicated, but also for getting us polynomial time algorithms. Because if you think about the domains we're dealing with, right? After refunctionalization, we start to have these domains like log to bool. Right, so what is log to bool? Well, the good news is that it's finite now, because log is finite and bool is finite. So we have now the need to range over every element in a domain log to bool, and the number of functions from log to bool is like 2 to the basically 2 to n if n is the length of the string you're parsing. Right, so as we parse longer and longer strings, the domain is going to be 2 to the n, big. So good news, it's finite at least, which is much better than what it used to be. But bad news is exponential. Right? But what's nice about having linear functions is that we can make that not 2 to the n, but 2 times n. And the reason is, if you have a lollipop, you can think of a function that only uses its input once as just a non-deterministic pair. Like in general, if you have some function from, let's say, a to b, right, but you only use this a once, then you can think of an a to b function as a distribution over a times b pairs, over ab pairs. Just for each a, you look at the distribution over b's that it will produce, and you know that you're never going to call this function again. So it's as if the function kind of guesses what its input is going to be, and once it guesses, it's just going to say that's my input. Okay. No, this is not. I understand this is very sketchy. The slides would not have helped, but here I'm here to help. Yes.
I'm not sure where linearity came in, because can't you say any function? You can like look at its graph and then
but what does it mean to sample such a function? You probably have a similar question. So what does it mean to, like, if I say pick a random, never mind log to bool. Like suppose I say please pick a random bool to bool function. How many bool to bool functions are there? You have to pick, like, do I mean the constant false function? That's one pick, or I could pick not. That's another function, right? So there's so many functions to pick, right? But if I know that the function will only be applied once to one input, then to pick a function is actually equivalent to picking a bool-bool pair. I could just decide, I bet my function is going to be called on false. And when that happens, I'm going to return true. And I don't even choose what my function is going to do when it gets called on true instead. Right, so that's the key. Okay, I hope that helps. It's also related to, I don't know.
So maybe a very sort of, I was trying to like explain what you were saying in sort of simpler terms. And I think one way to say it is, okay, you take your function, and then you can, we're all used to saying, oh, you can instead represent a function as a relation, as its graph. But then you're like, oh, but we don't, a graph would let you could sort of use, you could call it over and over again.
Yeah.
With lots of different spots in the graph. But instead you're saying, no, we're going to, since we're only going to call this once, then we only need one entry in the graph.
Yeah, exactly. Yes, you just pick the entry. Yeah.
And maybe you already know which entry it is.
You just non-deterministically choose, because these weights are going to sum to more than one. Yeah, you just predict, and you make all the choices at once, and then later on, if you get the wrong input, you just fail then. So you kill off the probabilities where you guess wrong later, but right now you just guess all those probabilities. Yes.
Right, so you're saying you can replace the function with a pair.
Yeah, with
basically,
one
not,
pair.
Not a set of pairs.
Yeah.
You can always pick with one.
Yeah, so instead of picking the not function, I non-deterministically choose between the false true pair and the true false pair. Yeah. Yes. So that gives us polynomial time. It recovers possible algorithms in the literature, some of which are people's dissertations from the 80s. And yes, so that's nice.
So where do derivatives happen?
So somewhere in the, okay, so it's in the solve part, basically, right? So solve, you could basically imagine taking those equations and taking the derivatives of those equations, and then you solve them. So instead of like, you might think, oh, I have a solver, it's written in PyTorch, I'm just going to let PyTorch automatic differentiation do the job. But the problem is that that solver has a fixed point in it, and you don't really want PyTorch AutoDiff to look into how that, like, to differentiate through the iterations of that fixed pointing. So instead, there's some custom AutoDiffing happening, where we say, you have some equations, you can solve them, but you can also first differentiate and then solve them. So you're differentiating the equations, not the solving process.
Okay. Well, I'm just surprised that, like, if you're differentiating, that maybe be, you're doing Newton's method or something, but that will give you approximate solutions.
Okay, so there's two parts of that. One is we call Newton's method exact, and the excuse, it's kind of like how people call sine or exp exact, even though maybe in your math library there's actually some iteration algorithm happening, right? Because we know how long to run the iteration to get a precise enough, numerically, like, precise. That's what we mean by exact, right? So I should have put a star for a footnote under the word exact. So yes, we call Newton's method exact because there are those papers with nice abstracts that give us guarantees about precision, about accuracy. I don't know. Okay, so the other thing is, right? We don't say do the Newton's algorithm and let AutoDiff do the job. Instead, we first differentiate and then we do a separate Newton's algorithm on the differentiated equations. Like, I don't know, I haven't tried doing this math, but maybe, like, you think about the equation from earlier, right? So it's this equation, right, from about W. Maybe you can just, like, take the derivative. Is that maybe one way to think about it? You take the derivative and now you have the equation on dW, not just W, something like that. Or you have a set of equations, you have one equation about W and another equation about both W and dW, and you solve them together. Something like that. Maybe. I've not thought about this way, but something like that. Yeah. Yes. Okay. And Yafei is going to help us, has helped us make that equation solving faster. Okay, thank you for coming.